Let me introduce the speakers. Adrian is a modern C++ enthusiast interested in the newest language standards and development of high-quality code, previously promoting music bands as a member of the board of Kompresor Foundation, as well as C++ at EPAM as a member of the board for its C++ community. Recently finished working on a commodity exchange trading system, currently taking a deep dive into machine learning at this company called Habana. And privately, he bakes his own bread, but I'm not actually sure how often he eats it. And Piotr, on the other hand, is a music and automation enthusiast. He's focused on efficiency and effectiveness, experienced in management, programming, and DevOps, and enjoys building simple solutions to human problems. Occasionally writes IT articles, never without headphones around, very often wearing sunglasses. He loves listening to music, especially with friends. He practices this extreme sport called parkour and also runs a book club. And from time to time, Piotr actually eats Adrian's bread and gives him feedback on his baking skills. But today they're going to be talking about cloud-native C++ modern architecture for modernized language. A round of applause, please, for Piotr Gaczkowski and Adrian Ostrowski.
Okay, hi there, people. I got to get this thing going. First of all, thanks for choosing this session. First of all, because it's late in the afternoon and I guess you're all tired. Second of all, because all the other sessions are at least equally interesting and probably maybe even more depending on your interests. But if you are here, I guess you'll be interested in what we have to say. As Rafał mentioned, my name is Piotr Gaczkowski, and if you want to check out the slides on your mobile device and watch them later, they should be available at the link above. Otherwise, if you're interested to looking for some more info about me, it's listed in here. Since my name is quite unpronounceable to foreigners, I often go by Doomhammer or Doomhammer NG, so that's the way you can find me.
And my name is Adrian Ostrowski, and I'm working at this company named Habana, just as Rafał mentioned. It's an AI processor company that creates hardware and some software for this hardware for deep learning, so accelerators for training and inference.
Okay. The idea and the deliverables that we want to give you today is that I'll set the stage. I'll do the bit of a warm-up, theoretical warm-up, saying things about cloud native, what it is, what it's good for, and things like that. And after the warm-up, Adrian will take you for a deep cloud dive, code dive in the clouds, showing you how you can use C++ to write cloud native applications. So, first question to you. How many of you have heard the term cloud native? Okay, I see some of you have at least heard it. How many of you knows what it means? Okay, a bit less hands, but still, it's fine. Yeah, so what is cloud native and why should we care? I'll deliver two definitions for you. One is the one that I particularly like and use it very often. The other is less funny, I would say, but maybe a bit more straightforward. So, cloud native is the 21st century rediscovery of the mainframe. And why should we care? Well, because Google uses it, right? Everything that Google uses has to be good. But let's start again. What is cloud native? Cloud native is and yeah, I know it sounds like a sales pitch and pretty bad one at that, is a vendor-agnostic way to deliver scalable and highly available applications. What do you mean by that? By that I mean that there are several standards on how to write applications, focusing mostly on the business logic and not on the stuff that has been already prepared by somebody else. For example, if you're using a public cloud like AWS, GCP, Azure, or whatever else, you also get some abstractions. You get load balancing, for example. You get virtual networking. You get access to on-demand instances, etc., etc., etc. But all of them works in a vendor locked-in manner. So if you start building an application on one vendor, you cannot easily move to the other. What does it mean for you? Well, it means that when you pass certain point, you will basically build enormous bills each month by using this cloud vendor. This happens a lot with some big companies, for example, like Lyft or the US government. It's also a big company, if I may say so. So vendor lock-in is a real problem. And the cloud-native approach helps us to use the same set of tools, but without the vendor lock-in. The idea is that those building blocks, those Lego blocks of software architecture, will be open sourced, accessible to anyone. You can run it on any cloud you want. You can run it on your own computer. You can run it on a Raspberry Pi, and you also can run it on your phone if you are adventurous enough. Why not? And why should we care? This would sound a bit like a sales pitch, but it helps to achieve the business requirements. So it helps to build the application to serve the customers, whoever they are, in a way that minimizes this vendor lock-in. Moving between vendors, between solutions, may thus become easier because they are loosely coupled, not strongly coupled. So, how did we come to the cloud-native approach? A brief history of application architectures. It all started with the start of computing. First of all, there were monolithic applications running on CPU because that's what the computers were for. You have the central processor unit, you have the program that you wrote especially for that computer with that peripherals. You have to handle all the interrupts yourself. You have to handle keyboard teletype, whatever there was on your own. And it was pretty tedious. So the next step was the introduction of monolithic applications, but running on an operating system. Operating system, in this way, functioned as a first abstraction layer. It abstracted the low-level stuff, the drivers, the interrupts, the memory management. So you could focus on writing the actual application, the actual thing that brings value to the user. And from that point on, this abstraction is constantly evolving. We abstract many other ways. If you have ever used any modern web applications, especially build one, you would probably find out that they consist of thousands of various dependencies, each of these dependencies forming another abstraction layer. So the developers can focus on what's important to them and not solve the problems that have been solved previously by somebody else. After monolithic applications, there came an advent of client-server applications. So basically, the logic was split between the one fat computer that processed everything and the slightly thinner computers that mainly was featuring the user interface. Still, this wasn't enough. After that, people thought that the client-server model is not suitable to every solution, to every project, to every product. So service-oriented architecture was developed, or specs, or whatever can you say about the architecture. And there are many different implementations of service-oriented architecture, but most of them assume that we have different services performing different tasks and communicating in one way or the other. One example would be the enterprise service bus, when we have this bus that processes the messages that we want to input into the system, and different services process those messages, returning the answer back to the service bus. Another approach to service-oriented architecture is microservices. And this is the approach we would focus later on. Especially, this is the part that Adrian will show you how to do in C++ in less than half an hour. So that's that. Benefits of microservices microservices allow us easier debugging, because when we have services that are micro, which means basically as tiny as possible, there is less code to debug. They do one thing and one thing only. The definition is that they should do it okay, but if anything doesn't work, we have a rather small surface to look at to search for problems. Then there's better scalability, because those services are usually loosely coupled, and we can just, for example, set up 5, 10, 20, or whatever number we want of those services to handle the larger volume of requests. Then there's better resource utilization. Assuming we have 3 powerful machines, if we have microservices, we can use the resources on those machines that correspond exactly to our needs. If we need more workers, for example, we're serving an airport, and we want to sell more tickets, but we are not necessarily interested in any other services. So we increase the number of microservices that sell tickets, and they just use the whole available computing power. We can also build anti-fragile systems, and for a moment I would like to pause here. Have any of you here heard the term anti-fragile? Oh, I see one hand, if I'm not blinded by light. Okay, so that would be fun to introduce. Normally we are talking about things that are fragile, that break easily, and things that are sturdy, that don't break easily. But sturdy is not an opposite of fragile. It breaks just the same way as the fragile thing does. It only needs more time or more force to break it. Whereas anti-fragile system is the one that benefits from the stress we put into it. Most natural organic things are anti-fragile. Most things created by humans are either fragile or sturdy. For example, if we have a statue, it's sturdy, but it will break at some point. If we have a human organism, if we cut ourselves, we will heal. If we rip our muscles during the training, they would not only grow back, they would also grow stronger. So that's the example of an anti-fragile system. And we can use it this way by leveraging microservices. In fact, that's what Netflix does with their infrastructure. Even creating microservices to cause disruption and to check what is going on after that. They call this the Chaos Monkey Army, I think, and basically it was the beginning of chaos engineering, which is something that I encourage you to look deeper into. It's an interesting concept. Oh, hi. Another thing, I'm not sure if it's a benefit of microservices, but it's certainly one of the features, is statelessness, hard word to pronounce. And statelessness means that we don't carry any state in these microservices. Why is it important? Because the less we have to care about state, the less problems we have. We just run our service. We can, cold boot it, and it's ready to run. Whatever we do, if it breaks, then it breaks, right? No problem. We can set up another one. There is no state we have to persist. It's a feature of microservices, but it's also one of the major headaches, because I have never, ever seen an application that is truly stateless. Oh, OK. Maybe apart from the calculator. You can write a stateless calculator that whenever you input 1 and 2 returns 3. But I guess that's as far as you can go. Most other services need some sort of state. And this is kind of a, shadow zone when it comes to cloud-native approach. So everybody knows that cloud-native is good. But if you have stateful applications, you have to be careful. So that's that. A brief history of software deployment strategies. I think this would be even briefer. With monoliths, it is obvious that manual configuration was used, because every piece of software was treated like a special snowflake, because it was a special snowflake. It was written for this actual machine. After that, when people started doing more deployments more often, and started seeing that this configuration can be automated, because it makes no sense to do the same set of manual steps each time we want to install a piece of software on a given machine, there came automated configuration management. Another part in the evolution, at least from my perspective, was the advent of pre-configured virtual machine images. So we wouldn't just get the machine, run some scripts on it to configure whatever the state we need, and then give the application. We would prepare an image that contains configuration, whatever else we need, initial data, the application, and then we only deployed it to the actual system. It made deployment a lot easier and a bit faster. But virtual machines came with one drawback. And that drawback was, as you may imagine, performance. Since they were virtualized, they needed much more resources than just the application would need. For example, we would need to boot the kernel, which penalized us with some time to boot it. Also, this kernel would have to use some part of memory. In most virtual machine environments, we also have to decide upfront how much memory we would like to give to this virtual machine and how much CPU we would like to give to this virtual machine. So scaling was possible, totally, but not very convenient, I would say. But after that, there came containers as a lighter alternative to virtual machines. So they also use a kind of virtualization, but on the OS level and not on the entire machine level. We have the same kernel, but other than that, everything is contained in a separate, container. And a quiz for you. I have, unfortunately, no gifts for you. If you know the correct answer, I can give you a bottle of water if you want. Do you know where does the name containers come from in terms of the application containers that we are speaking of? Anybody has a clue? OK, so just as the shipping containers that you see here revolutionized the modern transport and logistics, because suddenly there was only one thing you have to worry about. The same happens now to software development, application development. Containers give us the means to develop applications in whatever technology we like, but we still have the same way to run them, to configure them, to interface with them. So that's really convenient. Imagine how a shipping port looked like before the advent of containers. Each ship was different, each had a different cargo. You would have to move all those cargo to different places. And yeah, until recently, the same was with applications. The Java application required totally different approach to deploy than a C++ application. C++ application was something totally different to Python and to JavaScript and to whatever other technology there is in the world. So you have to have a deployment team that was skilled in each of the technologies used by the projects, and there could be many of them. So the benefits of containers are small overhead, as I said, standard interface, configuration bundled with an application, so we don't have to configure anything on top of that. We can build, test, deploy to production the exact same image. So it's no longer, works on my computer. If it works on your computer, there are high chances it would work everywhere else. And there is a common interface for all the technologies. So when you put containers and microservices together, because you can use them separately, you gain some cool things because they complement each other. And they both form the basis for a cloud-native approach. In cloud-native, we are mostly focused on containerized applications. We are mostly focused on microservices. So, cloud-native approach uses a set of standard interfaces to some common problems. As I said, the problems are listed. I won't go over that because there's not much sense. That's why it's worth getting interested in. If you have any of those problems, maybe a cloud-native approach might be a good solution to that, but not necessarily. And cloud-native is mostly connected to Kubernetes. You might have heard them, like in a tandem, both mentioned at the same time. But there are other projects, for example, Prometheus, Envoy that we'll come to in a moment, Core DNS, other things like that. They all have their use cases for cloud-native applications. For example, FluentD helps with creating a unified logging layer. Jaeger helps with distributed tracing, so getting data from different parts of the system and connecting them together, looking at performance of each application and what goes on in our services. But a part of those projects that I mentioned, there are also 15 incubating CNCF projects at the time. There are 20 sandbox CNCF projects. CNCF is a cloud-native computing foundation, I forgot to add. And the entire cloud-native computing foundation portfolio consists of like 1,300 projects around with a market capitalization of enormous amount of dollars and funding of enormous amount of dollars. So it's definitely something to be watching for, because, well, it's no longer that just Google uses it. I'm not saying that this is a reason you should jump into it, but watching it, I definitely can tell you to do it. So, back to the mainframe. Why is cloud native better than just getting IBM Zs and using them? Oh, by the way, I was recently looking at some cloud native and mainframe comparisons, and I realized that IBM actually advertises its Z-series mainframes as a gateway to cloud native. So I'm not sure. They're endorsing cloud native on mainframes. That's something I couldn't have imagined, because I consider mainframes to be a relic of 50s or something like that. Yes, so back to the point. Why is cloud native better? You don't have to learn COBOL to write cloud native applications. That's, for me, a very good reason. You can use C++. That's another good reason, because many people here use C++ on a daily basis, so you are already equipped to write cloud-native applications. And you can use a modern C++ as well with cloud-native applications. Actually, it's quite easy, as Adrian in a moment will show you. So, thank you for keeping with me here on this cloud-native introduction. Now, let's go for an actual code dive with Adrian, who will take you to the clouds and beyond.
Okay, so let's dive deep into the meat and let's make a microservice. So what do we actually need to create one? So we need some ingredients and we need some infrastructure, both of which are on this picture. And the ingredients would be the core application, and it should contain mostly, I mean, at best, it should only have the core business logic and some communication software components. So let's create a simple generator for code names, just like the Ubuntu system has. So, for example, the precise pangolin. And it's always an adjective plus an animal name. And our microservice will accept an input, which is a single letter, the first letter of the name. And it will output just the code name. So a possible output for the letter P would be pretty pig. And that's actually one of the proposals that it stays on Ubuntu's wiki page for 12.04. Maybe they will reuse it when they come to another P-named release. And for communication, for interfacing with the outside world, we can use the C++ REST SDK, which is well tested in battle. It's a Microsoft-created library that is able to create HTTP requests and responses for sending JSON messages. So how can our code look like? And here's an example. So we have a simple function to handle the incoming HTTP requests. What we are doing is we are just extracting the parameter. That is the simple letter. And if it's not there, we can return an HTTP bad request, error code, with an error message. And if the letter is there, then we can just generate the code name and pack it in a reply that says HTTP OK 200. So let's see how the respond function looks like. And this is really a simple function. It just gets the code and the returned string, and it packs them in JSON, and then uses the incoming request to reply to it. And our main function is also pretty simple. So we just create an endpoint. We are listening on every socket for the name on the name generator. And once we open the socket, we want to listen just for GET requests, so we register just for that. Then there would come some code to wait the listening and close the application. So yeah, so we created the application, but are we there yet? Is this already a microservice? Is this all that you're gonna need? And probably not, because this works. However, REST isn't the most performant choice. So if you've decided to write your microservice in C++, chances are you want to use something faster. You don't have time to use REST. So what can you use instead? And one of the technologies that is becoming really popular, and I think is a good choice, is GRPC. And this is a framework that is actually being developed as part of the CNCF that Piotr mentioned. And it has several benefits. Just like REST, it allows us to easily communicate with software written in other languages. So you can write other microservices in Java, Python, Ruby, C#, or even JavaScript, and they could communicate using gRPC. It's blazing fast, and underneath, it uses a chosen by you payload container. So it could be, by default, it's protocol buffers. And this is, I think, what we're going to use. There are other options, but this one is the best tested. Excuse me.
And it's pretty performant as well.
So let's see how the definition of our service in gRPC look like. And this is basically the same service that we had in REST. So as we could see, it's just a simple definition. We have a service name, generate code name, and it accepts a request, which we define just below the service. And then it says it returns a response, and we also define the response. So unfortunately, gRPC or the protobufs don't support single characters, so we're going to use a string as a letter. But I think it's not that common problem to pass a single character to a microservice. Usually you pass something more. So let's see how we could use it. So using this, using the tools that the protocompiler and the gRPC, we can generate lots of code that we can just use either to create a client for the service or to create a service interface that we later need to implement. So this is how we could implement our name generator service. We just inherit from this interface. And we create our name generator class. It has a function which is the same name that we saw on the previous slide. It's really simple, and it accepts the request and either returns the correct response or a status code that could indicate an error. And first we check if the input is valid. I'll save you that. And if it's not, we just return an invalid argument. It will get translated. So it's translated to another error code underneath, but let's leave it for that. And then if the input is OK, we just generate the code name using the input, set the reply field, and return a default OK value. So now our main function could look like this. It's also pretty simple. We just create our name generator service and then create a builder for the server in which we register our service, say that it has to listen on the given port, and we just start to listen and wait. So we have now this great performant gRPC service, but there is an issue because we already deployed our REST version before. So now we have to support it, right? Some folks are already using it. So should we now care about two versions and co-develop them in parallel? I think that's not the best approach. And there is a simple way to solve it, even without touching code. So let's move from the first ingredient, which was code, to the second one, which is infrastructure. And what we really need is an envoy to proxy between the REST interface and our new performant gRPC service. And let's focus on those two words here, envoy, proxy. So it turns out there already is something like this. It's Envoy that was mentioned by Piotr. And it's a library that was created by Lyft for cloud-native applications. It's open source in CNCF. It's a CNCF project, just like it was said before. It's high performant. It's all written in C++. And it can work well both for standalone applications or services and for big service meshes. So if you want to create some bigger infrastructure with, say, Kubernetes or Istio, it's also an excellent choice. But what exactly is Envoy? So what you can see on this image is a sidecar, and that's exactly what Envoy is. It's an example of the sidecar proxy pattern. So just like you put a sidecar, attach it to your motorbike to give the motorbike extra functions like more stability, more seats, the same way you can deploy Envoy and let it attach to your application. Oh, and by the way, the name of this picture is Lovely Combination, which I think is a pretty accurate name for combining both the sidecars to your motorcycles and to your software. So if you deploy them on your host, on your let's say in a container or wherever you choose, you have only those two components. You have the application that can now focus only on interfacing with the sidecar and writing its business logic. And the sidecar pattern, let's say an Envoy instance, one for each instance of your application, can interact with both the app and the outside world. So it can provide you with features like automatic configuration, service discovery, and lots of more. And this is great for you as an application developer because it means you don't need to implement those in your application. So it gets lots simpler. You don't have dependencies. You don't depend on libraries or any libraries that your libraries depend on. And Envoy has one good thing about Envoy is that in comparison to some Netflix services, in Netflix, you have to somehow integrate those in your application. So oftentimes, you need to rebuild your application when you update one of those Netflix components. And with Envoy, it's a totally different binary. It just communicates with it. So if you update Envoy, your application can stay the same. You don't need to rebuild it. OK, so let's now get back to our core problem and see how we can use Envoy as a bridge between our two services. And this is done using Envoy's configuration files. I think this is pretty easy and convenient, although it can seem a bit verbose at first. So Envoy basically has this concept of those filter chains, which is just a set of filters that do things with the incoming and outgoing traffic. So we have the HTTP connection manager filter, and this is exactly what provides us with a REST endpoint. And then we have to create a route that the traffic that goes through this filter will go to. And what we are going to do is we are going to route all incoming traffic, regardless of the domain written in the HTTP request, to our cluster. And this is the other part of that config. So let's name that cluster GRPC service. It will be a pretty simple one. And here you can see its definition. We have some timeouts for connections. We can set some load balancing or not. Round robin is the fine, simple default that tends to work. Not that others don't. Our cluster is defined like this. So we have to define all the endpoints that go into this cluster. We can have multiple instances, either on the local host or somewhere nearby. OK, and this just works. So now we have a bridge. But is that all? Do we have a complete microservice now? Some of you could say yes, but microservices usually require more than just some infrastructure and some core logic. I mean, this many infrastructure that we already had. So one of the most common issues with network architecture, distributed architecture, is that you need to sometimes handle lots of incoming load through the network. So lots of things can go bad, and you need to wait oftentimes for incoming replies to the requests that you're sending. And microservices like to make lots of calls to other microservices. And what should we do when the service that we are calling is busy or doesn't respond in a timely manner? If it just crashed, it's simple, right? We connect to it, we get a connection refused, so we know it's down. The worst case is when it still works, but it takes seconds to complete our requests, and thousands of them at that. So those long waits could cascade not only to us as a caller of this service, but also to other services that called us. And this is really tragic for our whole architecture. And the solution to this is to use this pattern named circuit breaker. And circuit breaking is basically to detect if a service fails to complete requests and then assume it's down and just short circuit, so stop waiting for the replies and just return an error immediately. So how do we do it in Envoy? And it's also pretty simple. So we have the circuit breakers section that we can add to the cluster's definition. We can prioritize some traffic and set different policies for different priorities. So in this example, we can define the max connections parameter, which is for HTTP 1.1 connections. Then we have HTTP 2, which is also supported by Envoys, and this is steered by max requests. And also there's this third max pending request that serves as a, well, just as its name suggests, it's for pending requests. And Envoy, unfortunately, doesn't provide us with an option to break on latency in the circuit breaker, but fortunately, it has another feature that can help us with this. And this other feature is automatic retries. So its main purpose is to just retry the request if we got an internal issue with the called service. So sometimes the services just hiccup, and it makes sense to retry the request. And we can configure what error codes we would like to retry the service request on, how many time we want to spend per each request, and how many of those retries should we do. So even though you see the 500 HTTP code here, it will work for our GRPC request as well, because there is a translation mechanism. So most of the GRPC failures will be retried if you set the config like so. And if per request timeouts is not what suits you, you can also, or instead, set a global timeout for all the requests. Another feature that you could find handy if you want to have microservices in production are incremental blue-green deploys. Basically, a blue-green deploy is when you have two environments and you switch between them. So you deploy a newer version of your application to one of them, and then switch it to production. If anything goes bad, you can always switch back to the working previous version. With incremental deploys like those, you can gradually switch. So first you can just deploy your application and start it and see if it doesn't crash. Then you can slowly start putting more and more traffic into it and observe how it behaves. Can it handle the load? Does it crash or not? And it's pretty easy to do with Envoy as well. So here for our name generator, we can just set a route that will move some traffic to the new version of the application. So here it's 5% of the traffic, and for the previous working version, 95%. And we can gradually increment this to 15, 50, and eventually 100. And is that all that Envoy can do for us? And it turns out it's not. It's actually a bigger beast. So one of the cool features that it also offers is service discovery. It can look for other microservices for us that we want to call. It can configure our application dynamically, so you can just either remotely connect to the admin panel of Envoy and set some parameters, or modify the config file and it should go live once you save it. Another feature is load balancing, so we already saw that round-robin policy. And yet another one is health checking, so we can either check if the cluster as a whole is healthy and processes requests well, or if there is maybe one instance in this cluster that behaves badly, and this is the outlier that we should remove. Another feature is backpressure. So this is mostly useful when your microservice is under heavy load. You can just return an error code early to not call the service at all and let it have some space to breathe. Yet another feature that Envoy offers us are tracing capabilities, and it can really well gather statistics and logs along your clusters and aggregate them along your services, along routes and nodes. And yet another one is request shadowing, and this one is interesting because sometimes you just want to grab some traffic from production and send it to your test environment to see how your test environment could behave. And this is what request shadowing exactly does. So you can either send all the traffic that you've got or just parts of it, and it just works. And also Envoy can be used to configure SSL and TLS between your services, or just as an entry point to your architecture, to your system. So it can terminate the user connections, the TLS connections coming into you. And it turns out that Envoy as a sidecar really does provide many, many features that you could find useful as a developer. And instead of baking all of those in your core application, you can just focus on writing some simple config files and the core functionality in C++. And it turns out that basically to create a microservice, all you need is C++, because you have your service in C++, GRPC and protobuf are also written in C++, Envoy is, so basically your whole software stack could be in this technology. And if you're into heterogeneous deployments, you can just as easily communicate with other microservices written in different languages using this approach. And since this could give you smaller containers because you don't need to, let's say, pack the entire JVM or whatever you want to pack there. And it also gives you C++'s performance. And with that, I think we are ready for some questions.
As ever, towards the end of a talk. So anybody, please, stairs, microphone, questions.